Okay, welcome everybody. It's New England Dynamics and Number Theory seminar. And our speaker is in New England now. It's Lam Pham from Brandeis. The title is Short Geodesics in Higher Rank Arithmetic Locally Symmetric Spaces. Welcome. Can you hear me? We can't hear you.
Hi, everyone. Can you hear me?
Now it works.
Thank you for giving me the opportunity to speak. I don't know. Should I start, or do you want to wait a couple minutes more?
I think we can start. It's 12:16. Why not?
So I'm going to speak about some joint work with Mikolaj Fraczyk from the University of Chicago, and I will also mention some previous work with joint with François Tilmany, who is in Brussels at the moment. So I will start by introducing the different topics of my talk. So first I will speak about the Lemmer's problem from the fountain geometry, then some stuff about hyperbolic surfaces, and finally a little bit of higher rank generalizations. So let's start with the Lemmer problem. Many people know about this, but some may not know about it. So I will first introduce the Mallet measure of polynomials. So P is a complex polynomial, has alpha 1 through d as the complex roots and the leading coefficient c, and we just define the Mallet measure of the polynomial P to be the product of the large all the absolute values of the roots that have absolute value greater than 1 times the leading coefficient. So you can of course restrict to having a monic polynomial, but because we'll be interested in algebraic integers, and we will often look at the minimal polynomials over z, you have to take into account the leading coefficient for this Mallet measure. For an algebraic number, we will then define its Mallet measure to be the Mallet measure of its minimal polynomial over z. So m alpha is m of p alpha. Now, some remarks. If alpha is an algebraic integer, then the coefficients are going to be integral. And so the Mallet measure is going to be either 1 for roots of unity or greater than 1. Lemmer's problem from 1933, which is now often referred to as a conjecture, is that there exists a uniform lower bound for all the algebraic integers which are not roots of unity. So m of alpha is strictly greater than 1 with a uniform lower bound for any degree and any algebraic integers which is not the root of unity. So this problem was stated in his 1933 paper, and to date there are only partial results in several different directions, but this is still considered to be widely open. So why is it considered widely open? We just try to compute different Mallet measures, and actually there is a candidate for the smallest one, which is this polynomial, and we have never found any polynomial, any algebraic integer with a smaller Mallet measure. It's widely expected that this should be the correct lower bound. So if someone ever finds something slightly lower, that would be quite interesting actually already. Generally speaking, we have some bounds. Depending on the conditions, you may get better bounds. So in terms of general bound, the best known to date is the following that is due to Dobrovolsky from 79, with a slight adjustment on the constants due to Routier from 96. So if you have an algebraic integer which is not an integer and not a root of unity, then you have this Mallet measure lower bound. You observe that the Mallet measure, this lower bound for the Mallet measure depends on the degree of alpha. So unfortunately, this bound does go to 0 as d goes to infinity. Now, that tells you as an observation that we need to that this conjecture is true for algebraic integers of a given degree. I will now talk about some variations of this conjecture, precisely the one that I will be referring to later on. Now, if you take an algebraic integer alpha, you will look at all of its different conjugates for its minimal polynomial, and you focus specifically on those which have absolute value greater than 1. In particular, those are the ones that are involved in the definition of the Malin measure.
Well, this is confusing. There are two alphas, so one of alpha is fixed and another is a parameter.
Oh, yes, sorry. I should have. Yes, that's true. The alpha,
So the alpha in
it should be z in C, such that p alpha z equals 0 and absolute value of z is greater than 1.
Okay.
That's correct. That's very misleading. Apologies. Thank you. So, given this S of alpha, okay, we can just fix it and look at instead look at the algebraic integers which have a fixed prescribed S, number of roots outside the unit circle, right? So we could just take the same conjecture and now allow for this epsilon to depend on the parameter S. And in this case, you can allow this conjecture to be true. If this holds for all S, right, then we will just call this conjecture little lemma, weak lemma. Okay, so often when S is fixed, I will refer to this as a lemma conjecture at some level S, because this is the labeling that I'm referring to in this work. And when it holds for all the possible S, I will call this the weak lemma conjecture. Already, this weak lemma conjecture is still open. Now, there's a special case, and so I will introduce the Salem numbers. A Salem number, it's an algebraic integer which is real, which is greater than 1, and is conjugate to its inverse, and all the other conjugates, and there must be some other conjugates, have norm exactly 1. So you have x, which is the Salem number, x inverse is conjugate, and all the others are on the unit circle. So in particular, the degree should be greater than or equal to 3 in this case. And you can observe from the set I introduced above that it's specifically the case of S equals 1, where you have precisely one root outside the unit circle. Okay. Now there's a slightly there's a slight adjustment, because I'm also requiring that the Salem number be a real number. But that's also, as you can see, this is also a consequence. So you have to, if you put S equals 1, it has to be real. Okay. So now I can just specify the lemma conjecture for level S equals 1 and refer to this as the Salem conjecture, which I call conjecture S. And the same conjecture is that there exists an epsilon such that every Salem number is greater than 1 plus epsilon. Now, as you can see from the best, the lowest Malin measure known, this is still open. Okay, because the smallest Malin measure known is that of a Salem number. Sorry. The lemma polynomial that I referred to here, this polynomial that has the smallest Malin measure, it should have been written. It looks like it went away. But this lemma polynomial, it's called the lemma polynomial. The alpha corresponding is actually a Salem number. So all the roots of this polynomial are on the unit circle except 2, one being alpha, which is greater than 1. And one being its inverse. And so from this perspective, because the smallest Malin measure known is that of a Salem number, it is sometimes thought that the Salem conjecture is the hardest case of the lemma conjecture. It's not actually the case necessarily, but that's a perspective on this conjecture. Now I'll switch from the number theoretic to the geometric aspect of this work and mention a few things about hyperbolic surfaces. So hyperbolic 2/4, it's a quotient of the hyperbolic plane by a discrete co-compact subgroup of SL2R. if you want to have a surface, you have to take SL2R, but I'm happy with the discrete subgroup of SL2R. The more general, the more specific case that I'm interested in this work is the case of an arithmetic orbifold, in which case I need to define an arithmetic lattice. So if you have G a semi-simple Lie group, in this case, you can think of SL2R as in the definition above. You take a discrete subgroup gamma inside of G, and such a discrete subgroup is arithmetic if the following holds. You have a separate algebraic Q group, G, that's bold G, defined over Q, such that its R points are going to be isomorphic to the direct product of your original Lie group times some compact subgroup, some compact group. And in addition, gamma, which is your group inside G, will be commensurable with the projection of the Z points of G. So the Z points of G will be defined to be G of Q intersect SL and Z for any embedding of G inside SLN. Now, commensurable means that, so if the group on the G of Q intersect SL and Z, I just call this GZ, then gamma commensurable with GZ means that gamma intersect GZ is a finite index in both. And so this definition actually makes it so that the definition of arithmetic is well defined and independent of the actual embedding. Okay. The typical special case people hear about is the case of SL2Z inside SL2R. But there are different cases that we are interested in. And in this case, we can extend this definition to a group G defined over some number field K by taking the lattice not in GR, but in the K tensor R points. So this is equivalent by using the restriction of scalars. And unlike SL2Z, we are interested now in co-compact arithmetic subgroups. So in SL2R, we only have up to finite index commensurability. The only non-co-compact arithmetic lattice is SL2Z, but those that we are interested in are those are co-compact and will give rise to compact Riemann surfaces. And so I will take gamma inside SL2R to be a co-compact arithmetic subgroup. How do I construct it? It's a well-known classical construction using quaternion algebras. As an example, there are different constructions, of course, some using unitary groups and orthogonal groups, but I will just focus on just giving the basic case of how to quickly introduce an arithmetic co-compact lattice in SL2R. So for those who do not know this construction, you take a quaternion algebra over a totally real number field K of degree D. So all the Archimedean embeddings of K are into R, no complex embedding. And for any place of your number fields, the quaternion algebra extends to either become H or M2R, the 2x2 matrices over R. And H here is the Hamilton quaternion division algebra. So this is general definition for central simple algebras. In this case, we just care about quaternion algebras. So when you look at the A tensor, the completion of K with respect to some embedding, either you get a split case and you get the matrix algebra over R, or you get the ramified division case and you get the Hamilton quaternion division algebra. The particular case for our construction is that if your quaternion algebra over your division over your number field ramifies exactly at one place, then when you take the when you tensor A with R over Q, what you will get is then one copy of the 2x2 matrices over R, and then D minus 1 copies of the Hamilton quaternions. The meaning of this is that from here, you can construct an arithmetic subgroup inside SL2R, which is co-compact. So how do we do this? You pick an order O inside your quaternion algebra A, and you take the elements of reduced norm 1 inside that order. So the elements of reduced norm 1, the reduced norm will correspond to the determinant if you embed your quaternion algebra inside a matrix ring. And so that's why the elements of reduced norm 1 in that quaternion algebra will then give you elements inside SL2R. Because then you can project onto the M2 of R factor. And if you take this construction, whatever happens in the division algebra factors will actually be compact. Okay, so now you see how this arithmetic subgroup arises as an example. And now we look at special elements inside this arithmetic group, gamma. The elements we focus on are hyperbolic elements. So the classification of elements in PSL2R or in SL2R as transformations, for instance, of the upper half plane is for hyperbolic, elliptic, and parabolic. I only care about hyperbolic here. So I'll just say that the transformation gamma is hyperbolic if the trace has absolute value strictly greater than 2. Now I will take lambda gamma to be the single eigenvalue that has absolute value strictly greater than 1. And here's the fact that relates the number theory to the geometry due to Neumann and Reed in 92. I should mention also Ted Schinberg here, even though he was not a co-author of the paper, he's credited inside, and Suri same year, which is precisely that this eigenvalue, the absolute value of the eigenvalue, which is strictly greater than 1, is a Salem number whenever gamma is a co-compact arithmetic lattice in SL2R. But in fact, you can reverse this, and every Salem number arises as such an eigenvalue for some hyperbolic element in some co-compact arithmetic friction groups. So it means that for any Salem number, you can find some division algebra, division quaternion algebra, such that once you do the previous construction, then this gamma will embed inside your this alpha, let me say, this alpha, which is your original Salem number, will then embed inside SL2R, inside gamma, inside SL2R, as the eigenvalue of some hyperbolic element. If you want to view this more geometrically, we can define the translation length of the element gamma to be simply 2 times log absolute value lambda, right, the largest eigenvalue. And in this case, this corresponds to the length of the closed geodesic in the quotient of SL2R mod SL2 mod gamma. So you take SL2R, you get the symmetric space, which is in this case the hyperbolic plane, and you quotient by gamma. You get a hyperbolic element will have an axis along which it acts as a translation, and when you project onto the quotient by gamma, that axis will become a closed geodesic in that quotient. And so here's the statement, the corresponding statement, which now becomes obvious, but which was not until the work of Neumann, Reed, and Suri, is that if you can find a uniform lower bound for all co-compact arithmetic lattices inside SL2R, then if you can find a uniform lower bound for the closed geodesics, that means that the Salem conjecture is true. Okay. Now, you should note that in this case, this uniform lower bound is for one group SL2R, but for all possible arithmetic lattices. Just close the window one second. So we have all the possible constructions for arithmetic lattices, but we need to have a uniform lower bound. Okay. Now I will try to drift towards the higher rank case and mention Margulis conjecture, which I will, in this case, call conjecture M. So here's the conjecture. This is in page 322 in Margulis' book. You pick your favorite connected semi-simple algebraic group over R and take the R points. And there exists a neighborhood of the identity. There should be a neighborhood of the identity such that any irreducible arithmetic co-compact lattice intersects this this neighborhood of the identity only in elements of finite order. You can also phrase this by taking your lattice to be torsion-free, so it has no elements of finite order, meaning that this intersection is trivial. So you would be able to find one neighborhood of the identity which avoids all the co-compact lattices. I should mention that, technically speaking, this is not the exact statement in Margulis' book. Margulis' book has a statement asking for the rank, the real rank of G, to be greater than or equal to 2, due to the fact that in rank 1 we have non-arithmetic lattices. But what really matters from the perspective of the previous number theoretic conjectures that I gave is the fact that this lattice is arithmetic. So by replacing real rank greater than 2 with arithmetic, we can include the case of SL2R for this. But of course, we also include other groups such as the SON1. But there is work that suggests that this is also true. So let me just rephrase this in terms of geodesics. You take a semi-simple real group, maximal compact subgroup, and you fix your Riemann metric on the symmetric space, G mod K. And then you take all the possible arithmetic compact lattices for this fixed metric, and there should be a uniform lower bound for the closed geodesics of every hyperbolic elements. So L of C gamma here is the length of a closed geodesic in the quotient, just like before, where you have the same correspondence in SL2R as in any semi-simple Lie group, where if you take a closed geodesic inside this double quotient, it is in one-to-one correspondence with conjugacy classes of hyperbolic elements in gamma. So why did we modify this conjecture to replace rank with arithmetic? Well, that's precisely because Margulis actually observed in his book that the conjecture, the weak lemma conjecture, implies his conjecture. So that's since this is the case of level 1 corresponds to the conjecture for Salem numbers, it makes sense to introduce to include this case in this conjecture. But there's also some for the audience, there is also some recent work from Emery, Radcliffe, and Chance that shows that you have a similar, slightly different, but similar correspondence between Salem numbers and length of closed geodesics in SON1, in some arithmetic lattices in SON1. In their case, the lattices are often non-co-compact, but I'll just leave it there. In earlier work with François Tillmanier, we actually showed that this conjecture of lemma for all level S, despite being weaker than the lemma conjecture, is actually equivalent to Margulis' conjecture for all semi-simple real groups of fixed type. What does this mean? It means that if you fix your group, you type of your group A, B, C, D, E, F, or G, then if Margulis' conjecture holds for all the groups, for all the semi-simple real groups of a fixed type, then the conjecture of the weak conjecture of lemma does hold. So to go from the weak lemma conjecture to Margulis' conjecture, you need to use the Margulis arithmeticity theorem. But to go in the other direction, you need to observe that having this geometric analog allows you to recover all the possible algebraic integers that you need in order for this conjecture to be stated as such. So in fact, with the François Tillmanier, we are able to do it for every possible type, meaning that if you feel more comfortable working with some specific groups, then you can show Margulis conjecture for this particular group, then it will actually be immediately true for all the possible groups. So if you can show it for SLN, for all the for any SLN, then it will actually then be true for it will then be true for SON1, SP2N, and so forth. And actually, I don't know if there are any fans of exceptional groups here, but this also would be true for arithmetic symmetric spaces in exceptional Lie groups. So. Okay. Now let me try to relate a little bit more all these different conjectures to see what can actually be said beside this correspondence. So if you take Margulis conjecture, you are given a semi-simple group, okay? And of course, if you pick that semi-simple group to be SL2, this is exactly the statement before. And the statement that Margulis conjecture implies the Salem conjecture for SL2 is precisely this short geodesic conjecture, the equivalence of which was given by Newman, Reed, and Suri, right? But the other case is also true, and that's the result that I want to speak about a little bit more today. That's the joint work with Mikolaj Fraczyk. If actually you pick your group to be a simple Lie group, in this case SLN, actually Margulis conjecture is equivalent to the Salem conjecture. So it's very subtle. The different ways that you view these conjectures, it's very subtle. And if you take SLN, right, you may think that by so if you can prove the conjecture for SLN, from Margulis conjecture for SLN, then you will get the weak-lemma conjecture. But that's not true, because you have to show it for the family needs to be fixed, but in this case the Lie group is fixed. So when here you have to prove Margulis conjecture for semi-simple groups of fixed type, it actually means that you have to be able to prove it for products as well. So you need to be able to show it for products of SLNs. So if you were to be able to show it for just SLN, then actually if you prove it for SL3 or SL4, it doesn't matter because it's exactly the same. That's what this result says. That the case of SL2 implies the short geodesic conjecture for all the SLN. Now, why is this? Does this lead to pause a little bit? Because if you look very carefully, right, in SL2 you have just one eigenvalue and its inverse for your elements, and so it's a very simple algebraic integer. Not that simple, obviously, because these are Salem numbers. But in higher rank, the eigenvalues could be just arbitrary algebraic integers. And so what this theorem states is that actually, well, despite the fact that you could have arbitrary algebraic integers for eigenvalues, then the fact that these eigenvalues give you a short geodesic, right, is only related to the case of SL2. And I will explain a little bit what's that distinction. Now, the way you want to think of this is that the small Salem numbers control the Malin measure of other small algebraic integers. Obviously not all of them, but specific ones that arise as eigenvalues of hyperbolic elements in arithmetic lattices of higher rank. So now I will try to focus a little bit more on these different geodesic and see how the main theorem works. So here is a general formula, for instance, for computing the translation length of a semi-simple hyperbolic element in an arithmetic locally symmetric space. So you take your G, bold G here is going to be an algebraic group over K, or over R, whichever one you want. And you take the corresponding Lie group, and you take a maximal compact subgroup K and form the symmetric space. And again, you take an arithmetic lattice and take that quotient. If you take a hyperbolic element gamma, you then can see that it actually gives a closed geodesic in this quotient. And the way to compute its length, well, you compute it using Riemannian geometry, of course, but because gamma is arithmetic, it also makes sense to have a formula that involves some more arithmetic algebraic data. So the data that it involves is as follows, and that follows from the work of Pasadena Pinchuk on weak commensurability of arithmetic locally symmetric spaces. The length, the square of the length is going to be the sum of the squares of log lambda gamma, and lambda gamma is the value taken by a character, lambda, lambda being a root in the absolute root system of G. So the maximal torus here, T, is going to be a maximal torus that contains gamma. Here's our theorem, which actually is weaker than the previous theorem. If you pick a semi-simple Lie group without compact factors, and you have an arithmetic lattice which is irreducible in this semi-simple Lie group, and has trace field K, meaning that you can realize it inside, well, you can realize its commensurability class inside the OK points of an algebraic group defined over a number field K, where OK is the ring of integers of K. And if you take a semi-simple element gamma, you can look at the subgroup generated by gamma, so the set of powers, take the Zariski closure and the connected component of that Zariski closure, and you have a torus. Now, if this torus has rank greater than or equal to 2, then we can actually find a lower bound for the closed geodesic. And what you should see here is that there are some constants. In this case, the constants, they only depends on the dimension of G, but this lower bound that you see, you can see that it actually is a very large lower bound. So the closed geodesics that are short, that are small, that make the problem of this short geodesic conjecture hard, are actually geodesics corresponding to elements gamma only generating one-dimensional tori. Okay. So this, in a sense, this says that in some sense, without counting multiplicity, you can actually find a lower bound for all the possible geodesics. Now, another thing you can notice is that this the degree K has to obviously go to infinity, because you're taking an infinite family of arithmetic lattices. Okay, so this is the lower bound that we have. Now, I just explained that if the length of the closed geodesic corresponding to gamma is short, then gamma must be actually contained in a one-dimensional torus. But this falls short of showing that actually this is the same as only having Salem numbers. Precisely, if your group G is semi-simple, okay? And so you know that if the rank of the torus is greater than 2, then you're going to have a very large lower bound. But in higher rank, you can have a lot of different ways that you have one-dimensional tori. You don't know necessarily that these are Salem numbers. And actually, there's nothing to suggest that they are necessarily Salem numbers. Okay. So how do we return to the Salem numbers? Well, we need to understand how this length is built. And so we try to understand its components. So to understand its components, we can introduce a different quantity, the logarithmic Mallow measure of the element gamma. And this logarithmic Mallow measure will play the role of the length. Now, one has to be careful in terms of how we define different quantities in this case, because you're defining the Mallow measure of this gamma, and you would like to say that this Mallow measure is like the length of the corresponding closed geodesic, right? But you have to be careful because the way that you define the Mallow measure, there are different constants involved. And so the problem is that in passing from one quantity to another, you may bring in quantities which either go to infinity, parameters which either go to infinity or to zero as the degree goes to infinity. So in this case, you can see that I have picked the logarithmic Mallow measure to be defined from the root system. Okay. So how do we do this? We take the root system of G, the absolute root system, and we just take the sum of all the Mallow measures of all the values of the characters of the roots at gamma. Now, the thing that you need to observe is the fact that because gamma is an arithmetic lattice, then these values chi of gammas are actually algebraic integers. Okay. Now, here's the main technical observation of this paper. It's to observe that when you have the length of a closed geodesic, which is built up from this root system, actually some pieces of this length are related to one another. So we have the following result. Now, for every epsilon positive, there exists a number such that if you take any element of infinite order and you take the trace field, the field of definition of your K group for your lattice to be greater than this fixed constant, then any short geodesic will force some of these components to be multiplicatively dependent. Now, there's no reason why they should be multiplicatively dependent in the general case. It's precisely because the geodesic is short. Okay. Now, why is there this dichotomy between the short and the longer geodesics? I'll get to this in a moment. And we do this by introducing a higher dimensional version of the Lam problem. So what does higher dimensional mean in this case? Let me state this. If alpha is an algebraic integer, I have another quantity which is often associated to alpha, which is its logarithmic Veil height, and that's simply the Mallow measure rescaled by the degree. Okay, I have this kappa of n, which is just an arbitrarily well-chosen large constant of n, and we have the following beautiful results of Diophantine geometry due to Amoroso and David, which says that for any n, there's a number c, such that for any vector in GM to the power n, whose coordinates are multiplicatively independent, the product of the heights of the coordinates actually has some well-defined lower bound. And we will look at this result and use this result just in the case n equals 2. So that the result from Diophantine geometry actually has a beautiful set of problems associated to it, including a higher dimensional version, an appropriate version of the lemma conjecture. So here we will just take n equals 2, and we will take two elements, alpha 1 and alpha 2, and we'll just look at the product of their Mallow measures, or in this case, the product of their heights. Obviously, whether you take heights or Mallow measures, you have to pay attention to the scaling by the degrees. Okay. And in order to do this, we need to understand precisely the dependence of this lower bound more explicitly. So this lower bound depends on the degree of the algebraic extension generated by this pair. So in this case, what we will need is to understand the algebraic extension generated by the different values of the characters at gamma. And here's a technical bound that you need to have, which is that this degree actually only depends on the degree of the trace field up to multiplicative constants. These multiplicative constants, what we need is that they be depending only on G, the corresponding algebraic group or the Lie group that you have. Now, in this case, they do depend on it explicitly, just from the theory of algebraic groups, and actually they only depend on the dimension. So how do we actually use this to obtain Salem numbers from short geodesics? So you observe first that the reason we focus on multiplicative dependence of algebraic integers is because if you have a Salem number, then the conjugates are alpha and alpha inverse, which are obviously multiplicatively dependent. Okay, and so you need to be able to upgrade multiplicative dependence to that to obtain Salem number. That's the goal. So let me give a few details about how this is done in the abstract. If you take an element gamma, which is semi-simple and precisely lies in the arithmetic lattice, now you can look at the splitting field of the minimal polynomial of this of at gamma. So actually, the splitting field is well defined and independent of the representation chosen, but we fix the representation to be the adjoint representation. Now you have this splitting field of this element gamma, okay, and you can use this splitting field as follows. So you take a simple algebraic real group G, and you look at the value of a character chi of gamma. And now this value chi gamma, you want to assume that, of course, the absolute value is greater than 1, so that you're always focused on the correct short geodesics, those which do not give you a Marlow measure of 1. And now you can construct out of this alpha an appropriate number, which becomes a Salem number. So in this case, how do we construct this number? We just use the following construction. We just take the product of all these conjugates over an appropriate Galois group. So what is this Galois group? It's the Galois group of the splitting field K gamma over some other extension of K. So the extension of K is going to be obtained by taking alpha to some power and taking that algebraic extension. Now, this power P can be very, very large, but it's the advantage of this construction is that the product of these conjugates will not depend on how large this actual power is. And in fact, here are a few remarks about this. Alpha to the power P itself is also a Salem number. So it says that, in particular, when you have a short geodesic and you look at the components of it, then some large power is going to be a Salem number. So for instance, you could think of it as a, I don't know. I don't know how else to think of it. Some large power is a Salem number. But actually, the interesting fact is that when you take the extension over K, this only gives you a quadratic extension, regardless of how large this power is. And so once you have fixed this extension K gamma over K alpha P and constructed this new element alpha out of alpha, this is going to be a Salem number. So I'll stop here, and if you have any questions, please let me know.
Okay, thank you, Lam. Let's give a round of applause. Any questions?
I'll stop sharing.
So what is the, I mean, just remind us what is the diagram of all those conjectures?
The diagram of all these conjectures is essentially focus on the conjecture S.
Mm-hmm.
Right? Focus on conjecture S. If you know that the Salem conjecture is true, then this is equivalent to finding a lower bound for SLN, for closed geodesics in SLN.
Mm-hmm.
But whether you take SL3 or SL100, this is actually going to be the same. It's all going to be about Salem numbers in the end.
Mm-hmm.
There are some more precise results in the paper, in the papers of with Francois and with Mikolaj, where it all depends. The general case depends on the signature of your algebraic group or on the number fields that is defined over. So the number of real factors and the number of complex factors. So that's how you sort of level the conjecture. So the lower bound, you can first set by simply counting all the roots are outside the unit circle. But when you focus on the number of real roots versus the number of complex roots, then you get to actually observe this occurrence of Salem numbers.
Mm-hmm. Okay, but it doesn't say that conjecture S and conjecture L are equivalent.
It says that when you look at conjecture L of S,
yeah, for L of S, I understand. Okay.
Right? If you take conjecture L of S, right, it looks at the number of roots outside the unit circle,
Mm-hmm.
right? But if you have, for instance, of all these roots are outside the unit circle, if all the roots are real, then actually it does reduce to Salem.
Mm-hmm.
Because you can construct out of these roots, you can construct one single group that captures all of them. Mm-hmm. If you take a very large simple Lie group, right? Then if you look at all the possible algebraic integers you obtain as eigenvalues of hyperbolic elements, then all of these will at some point to a certain power become Salem numbers.
Mm-hmm.
Right.
Okay. Any questions, comments?
I have a very quick question. So if, so you mentioned this conjecture of Margulis, where you have this epsilon, which works for all arithmetic compact lattices in a given Lie group. Right. So does it follow from your work that so if this conjecture is true, then this epsilon would be independent of the group as well, or so there would be unique?
Yes. So that's from the in different ways. That's from the work with Francois. So if you take your semi-simple group G, right, and you prove the conjecture for this group G, then you can just take the exact. You can just take a group G that is similar to that one in some parameters, but that's of a completely different type.
Right, and the same epsilon would work, right?
Right, the same epsilon would work, exactly. The same epsilon would work. The S parameter will become involved in some. The S parameter, it depends on. It becomes related to the number field that you take, that is a K form of your real algebraic group.
Okay.
So as long as you can create an algebraic group out of a number field that has the same signature, then you can obtain the same epsilon for these different groups. And in the paper with Francois, we actually do it for every single family of groups, every single type, every single form.
Okay.
Right.
Okay. So, thank you.
Okay. Well, if there are no other questions, let's thank Lam again for a nice talk.
Thank you.
Thank you.